In this episode, we're going to take a careful look at feature selection, because choosing which inputs a model should rely on is one of the most powerful ways to improve trustworthiness without chasing flashy complexity. Feature selection can sound like a shortcut, as if you were trying to make modeling easier by throwing information away. But responsible feature selection is really about removing distractions and redundancy so the model can learn clearer patterns. Beginners often collect every available column, assume more is better, and then feel confused when the model behaves unpredictably or becomes hard to explain. The truth is that more features can create more noise, more leakage risk, and more opportunities for the model to memorize quirks instead of learning stable structure. A thoughtful approach uses evidence to decide what helps and what hurts, and it does that without falling into the trap of selecting features based on future knowledge. When you learn to use importance, correlation matrices, and VIF properly, you gain a repeatable way to simplify models while keeping them honest. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A responsible starting mindset is to remember that feature selection is not a beauty contest for columns, but a decision about what signals you want the model to treat as reliable. Some features are useful because they reflect real behavior that repeats, like the rate of failed authentication attempts relative to overall attempts, while other features are useful only because they accidentally line up with the label in the training window. Some features are redundant because they are different measurements of the same thing, and redundancy can make training unstable or make explanations inconsistent. Some features look informative only because they are proxies for the target, which is another way of describing leakage. Feature selection is how you reduce those risks by limiting the model's freedom to latch onto fragile shortcuts. In many real deployments, including security monitoring and operational analytics, it is often better to have a model that is slightly less accurate on paper, but consistently understandable and stable over time. That stability comes from choosing a feature set that represents true structure rather than incidental artifacts. The first tool people reach for is feature importance, and it is valuable as long as you treat it as a clue rather than a verdict. Feature importance is any method that estimates how much a model relied on a feature to make predictions, but different models define reliance differently. Some models have coefficients that act like weights, some models have split-based measures, and some models require separate techniques to estimate influence. The common beginner mistake is to see a ranked list and assume it is an absolute truth about causality or about what matters in the real world. Importance is only about the model you trained on the data you gave it under the evaluation setup you used. If your data contains redundancy, the importance can be split across correlated features, making each one appear less important than it truly is in a group. Responsible use means you interpret importance in context, then verify it with additional checks rather than deleting features based on one list. Another reason importance requires care is that a feature can look important for a bad reason, such as encoding identity, capturing a post-outcome artifact, or reflecting a logging quirk that changes later. For example, a field that is populated only after an investigation might appear extremely predictive, not because it predicts risk, but because it records the consequence of risk. A naive importance ranking would celebrate that feature, and a careless selection process would lock it into the model, creating a system that cannot function when deployed at decision time. This is why importance should always trigger a timeline question. Would this feature value exist at the moment you intend to predict, and would it be stable under realistic operations? If the answer is uncertain, the feature should be treated as a suspect even if its importance is high. Conversely, a feature might be genuinely valuable but appear low importance because it is masked by a stronger correlated proxy, which means removing it could reduce robustness later if the proxy drifts. In responsible selection, importance starts the investigation, but it never ends it. Correlation matrices are the next tool, and their main job is to make redundancy visible before it becomes a modeling problem. A correlation matrix is a table of pairwise correlation values between numeric features, and it helps you see which features move together in the data. When two features are strongly correlated, They often represent the same underlying factor, such as two different measures of traffic volume or two different time windows of the same activity. If you include many correlated features, some models will become unstable because they cannot uniquely decide how to distribute credit among them. Even in models that tolerate correlation, redundancy can inflate the feature space and make importance rankings misleading or inconsistent. For beginners, the key is that correlation is not automatically bad because real-world signals are often related, but high redundancy can waste capacity and complicate interpretation. A correlation matrix helps you spot clusters of near duplicates so you can decide whether to keep one representative feature, combine them, or redesign them. Correlation matrices also help you detect a specific category of beginner mistake, which is accidentally including multiple versions of the same feature created during preparation. It is common to have raw counts, normalized counts, rolling averages, and cumulative totals all derived from one underlying series, and many of those will correlate strongly. If you keep them all, the model can become sensitive to small variations in how those features are calculated, and that sensitivity can show up as surprising behavior when a pipeline changes. When you see a block of features that all correlate, you can ask a more meaningful question: which representation best matches the decision context, and which is least likely to drift? Sometimes the answer is the most recent window feature because it reflects current behavior, and sometimes it is a ratio because it normalizes across entity size. The correlation matrix is not telling you to delete everything correlated. It is telling you to acknowledge you have multiple ways to say the same thing. Responsible selection uses that awareness to simplify and stabilize. A critical detail is that correlation has limits, and beginners should not assume it captures every dependency that matters. Correlation is most straightforward for linear relationships between numeric variables, but many important relationships are nonlinear, and many features are not purely numeric in meaning. Also, correlation can be distorted by outliers, and it can change across groups or across time periods, which is a common reality in operational datasets. This means a correlation matrix is best used as an initial map of redundancy, not as a complete description of dependence. It also means you should avoid using correlation to justify dropping a feature that is conceptually important without checking whether it carries unique information in certain ranges or certain segments. In security analytics, for instance, two features might correlate during normal operations but diverge during incidents, and that divergence could be exactly what you need. If you drop one based on overall correlation, you might remove the feature that distinguishes critical cases. Responsible selection treats correlation as a lens, not a hammer. Now we can introduce VIF, which is one of the most useful tools for diagnosing multicollinearity when you are using models where interpretability and stable coefficients matter. Variance inflation factor, VIF, measures how much the variance of a feature's estimated coefficient is inflated due to correlation with other features. In plain terms, it answers the question of whether a feature is predictable from a combination of other features, which would make its unique contribution hard to estimate reliably. When VIF is high, it suggests the feature is part of a redundancy web, and coefficient estimates can swing dramatically depending on small data changes. This is especially relevant when you rely on coefficient interpretation because unstable coefficients can lead you to tell inconsistent stories about what drives predictions. A common beginner misunderstanding is to treat VIF as a magic number that tells you exactly what to drop, but it is better used as a diagnostic signal. Responsible use means you use VIF to identify redundancy patterns, then choose an action that preserves meaning while reducing instability. VIF also has constraints that matter, and beginners should understand them before treating it as a universal rule. VIF is typically discussed in the context of linear models, where you are estimating coefficients and their uncertainty, so it aligns naturally with models where multicollinearity is a direct issue. If you are using highly nonlinear models, VIF can still hint at redundancy, but it may not map as cleanly to actual model instability in the same way. VIF also depends on the set of features you include, which means it is not a fixed property of one feature. It changes when you add or remove others. This is why the responsible workflow is iterative. You diagnose multicollinearity, adjust the feature set, and then recheck, rather than calculating once and assuming the problem is solved. Another subtle point is that VIF can be influenced by how you encode categories and how you transform features, because those choices change correlations. If you use VIF, you should do it after your intended encoding and scaling choices are in place, and you should interpret it in that final representation. A responsible feature selection process also needs to distinguish between removing redundancy and removing weak features, because those are different goals with different risks. Removing redundancy is about keeping one of several near duplicates so the model has a cleaner signal and you have a clearer explanation. Removing weak features is about eliminating inputs that add noise or do not contribute meaningfully to prediction. Importance rankings can help you identify weak features, but you must be careful because a feature can look weak simply because the model has not been tuned well or because the feature's value shows up only in certain segments. In rare event problems, weak-looking features may still matter because they are informative only for the rare cases you care about. Correlation matrices and VIF help mainly with redundancy, not with weakness, which is another reason not to rely on a single method. Responsible selection treats these tools as complementary, so you are not using the wrong tool to answer the wrong question. Another key responsibility is avoiding selection bias, which happens when you use information from validation or test data to decide which features to keep. This is a subtle form of leakage because your feature set becomes tuned to the evaluation data, making performance look better than it would on truly unseen data. The safest rule is that feature selection should be treated like model training. It must happen inside the training process and be validated honestly. If you pick features using the entire dataset and then evaluate, you are no longer measuring generalization, you are measuring how well your choices fit that dataset. This is especially risky when you use target-based statistics, such as selecting features because they correlate with the label across the full dataset, because that directly uses label information from the evaluation portion. Even if you do not intend to cheat, it is easy to do it accidentally when you are eager to simplify. Responsible practice is to choose features based on training-only analysis, then confirm stability through cross-validation or time-aware validation that repeats the selection process properly. It is also important to recognize that feature selection can change model behavior in ways that are not visible in a single overall metric. Sometimes dropping features improves average accuracy but worsens performance on a critical subset, such as new users, rare categories, or specific time periods. Sometimes dropping features reduces false positives but increases false negatives, which can be unacceptable depending on the decision context. This is why responsible selection should include segment-aware evaluation, where you check whether performance remains acceptable across meaningful groups and across time. In operational environments, the cost of errors is often uneven, and a feature that looks noisy overall might be essential for a high-risk segment. Correlation matrices and VIF can help you simplify without losing unique signals, but you still need to validate that the simplified feature set supports the outcomes you care about. The point is not to keep every feature, but to avoid simplifying in a way that breaks the model's usefulness where it matters most. A practical way to think about responsible selection is to frame it as a set of commitments you are making about the data-generating process. When you drop a feature due to redundancy, you are betting that the remaining feature will continue to capture the underlying factor reliably over time. When you drop a feature due to low importance, you are betting that it does not carry unique signal that will become relevant under slightly different conditions. When you keep a feature despite correlation, you are betting that it contributes unique information in certain regimes that your model needs. These bets are not purely mathematical, because they depend on domain knowledge and on how the system can change. In cloud operations and security monitoring, systems are updated, logging evolves, and attacker behavior shifts, so stability matters. Responsible feature selection combines statistical evidence with a sober view of how the environment can drift, and it prefers features that are meaningful, consistently recorded, and hard to game. Another beginner misunderstanding is to treat feature selection as something you do once at the beginning, but in real work it is often an iterative process that evolves as you learn more about the data and about deployment constraints. A model might start with a wide feature set to explore what signals exist, then be simplified as you discover redundancy, leakage risks, and unstable measurements. As you update the pipeline, you might add new features that are more robust and remove old ones that were convenient but fragile. In time-aware problems, you might discover that some features behave differently across periods, which can motivate selecting features that generalize better even if they are not the top performers in one window. This iterative view is important because it keeps you from becoming emotionally attached to a feature just because it helped in one experiment. Responsible selection is a continuous refinement towards stable, explainable, and operationally realistic inputs. That refinement is part of earning trust, because stakeholders can see that the model's signals are chosen for reliability, not for short-term score chasing. When you put importance, correlation matrices, and VIF together, the workflow becomes less mysterious and more like a careful conversation with the data. Importance tells you what the model is using, which helps you spot potential leakage, suspicious shortcuts, or features that dominate too strongly. Correlation matrices show you which features are saying the same thing, which helps you simplify without losing information and reduces the confusion that redundancy creates. VIF quantifies how much redundancy is undermining stable coefficient estimates, which is especially useful when you need interpretable models with reliable stories. None of these tools should be used in isolation, and none should override common sense about what is knowable at prediction time and what is stable in the environment. The responsible goal is not the smallest feature set, but the clearest feature set that still captures the important signal. When you achieve that, models tend to train more smoothly, explanations become more consistent, and performance becomes more stable across splits and time windows. By the end of this topic, you should be able to treat feature selection as a reliability practice rather than a scoring trick, because the feature set is where many modeling failures begin. Importance is a useful guide to what the model relies on, but it must be interpreted carefully because it can be distorted by redundancy, leakage, and model-specific definitions of influence. Correlation matrices reveal redundancy and near duplicates, helping you simplify the feature space and reduce unstable behavior, while still requiring judgment because correlation does not capture every meaningful dependence. Variance inflation factor, VIF, provides a targeted way to diagnose multicollinearity in settings where coefficient stability and interpretability matter, while reminding you that thresholds and decisions must be applied thoughtfully. Responsible selection keeps evaluation honest by avoiding selection leakage, and it checks performance across time and groups so simplification does not harm the cases that matter most. When you build these habits, your models become easier to understand, easier to maintain, and more likely to generalize in the messy environments where data AI systems actually live.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.